The third and final segment on electricity and magnetism will cover batteries and the electromagnetic spectrum. We will ask, what are batteries? And what is a magnet? Then we will carry out 3 foundational physics experiments. And finally, we will look at the electromagnetic spectrum. The world is moving toward constant heat balance, the second law of thermodynamics. But in the meantime, we can unbalance electrical charge to make things move. We saw how power companies use generators to unbalance charge and then to pump it to the city, to your home, to the outlet, to the train. A power we largely take for granted. But there is another device that we use to unbalance charges and to pump them. A portable device that you can even carry in your pocket. Batteries. With it, we can unbalance charge and make things move, apart from our immediate connection to the power company's generators. A battery is a charge pump, a chemical charge pump. It chemically forces charge to separate out to negative and positive, creating an imbalance, a voltage. By connecting the two ends, you allow the charges to come back together again and balance. Modern batteries are just fancy versions of the first battery. Alessandro Volta made the first modern battery by stacking zinc and copper plates with salt or vinegar-soaked leather or paper in between the plates. You can make a simple and similar version of Alessandro Volta's battery, also called a voltaic pile. Soak several pieces of cut cardboard in an acid, like vinegar or even cola. A piece of foil serves as the contact for the bottom of the voltaic pile. Start the pile with a penny, then a zinc washer, and then a piece of soaked cardboard. Repeat this for several layers, ending with a zinc washer. Incredibly, even just 2 cells produce a measurable voltage. I will remove the battery and attach alligator clips to this dollar store calculator. Clip one lead to the foil and the other lead to the top zinc washer. Using only 4 penny and zinc cells, we are able to run this simple calculator using Alessandro Volta's simple battery, his voltaic pile. Today's batteries are called wet cell and dry cell. Wet cells like this are used in car batteries and use water mixed with a 40% wet sulfuric acid solution. The wet solution is a bath where lead and lead oxide plates, like these, soak and produce a current. Put 6 of these cells in a battery and you have a heavy car battery. Heavy because of the lead. In this battery, lead gives up the electrons and the lead oxide accepts the electrons, producing the imbalance. Each cell produces 2 volts. 6 times 2, you have your 12-volt car battery. When the battery is dead, it is fully balanced, no voltage. But when you buy them from the store, they are brand new and are imbalanced, producing the needed voltage. Those are wet cell batteries. They use a liquid for their acid. This is a dry cell battery. It doesn't use a liquid for the electrolyte, but rather mixes it into a sort of paste. Many periodic table combinations can be used as batteries, but the least expensive is the zinc and carbon battery. If it says batteries included, it is usually these inexpensive zinc-carbon types. Unfortunately, they aren't very strong, and the outer zinc can gets thinner through time and will eventually leak acid into your device. That's the white, crumbly substance you often see in a device after you've left the battery in there for a long period of time. But the most popular modern dry cell battery uses an alkaline solution on this end of the pH scale rather than an acid on this end. They are a bit more expensive, but they are stronger and they last longer. 8 out of 10 batteries sold in the US are alkaline batteries, not acid batteries. The elements used are zinc and manganese along with the alkaline paste. Here's how they are made. On the outside of an alkaline battery is a steel can. Then a paste of manganese metals is compressed into the wall of the empty container. The can conducts the charge for the manganese. This is the positive end with the button on top. A piece of paper or fabric now separates the manganese paste from the next chemical paste. This separator acts like the plastic separator we saw in the Leyden jar and acts as the cardboard or paper in the penny battery. The second chemical is a gel of zinc powder mixed with the alkaline electrolyte. The manganese loses electrons and the zinc picks them up. That's the movement of electrons. That creates the imbalance. To conduct the negative charge out of the middle of the battery, a brass pin is inserted and a metal cap put on. This is the negative end. The entire battery is then sealed in a plastic case with the company graphics. The common sizes are AAA, AA, C-cell, D-cell, and 9-volt battery. We've seen what's inside these round batteries, but what is inside a 9-volt battery? The answer is totally unexpected. Carefully pry the shell off, and remember to put on your safety glasses. And inside are 6 small 1.5 volt cells. The 9-volt cells are wired in series. They run one right after another to add their voltages. Just like a television series is stories that run one right after another, and they add up to one big story in the end. That's how a 9-volt battery is put together. By the way, technically, each one of these is called a single cell, a single electrochemical cell. When you put them all together, then it's called a battery. 2 or more cells together is a battery. So, technically, a 9-volt battery is a battery since there are several cells inside. And a single AA battery is actually a single cell. By the way, what about these big 6-volt lantern batteries? What's inside those? Another surprise! 4 cells making a real battery. These monsters are called F cells, and again, they were connected in series. If you need more power from your batteries, like an electric scooter, connect the batteries in series. Here, the voltage starts adding together. But the current, the amperage, stays the same, small. But if you need long battery life, like in your laptop computer, hook the batteries in parallel, positives to positives, negatives to negatives. In parallel, the voltage acts like there is only one battery, but the current, the amps, add up, giving long life to your 1.5 volts. Here's a simple example. This battery will run this light bulb for 1 hour. Add a battery in parallel and the bulb is the same brightness but runs for 2 hours. Add a battery in series and the bulb runs about twice as bright but for only 1 hour. And the main reason flashlight batteries are connected in series is because the tube design better fits our hands. While there are a lot of variations on how to make a battery or a cell, the way Volta separated and then pumped charge using chemicals is nearly the same way we do it today. What is a magnet? This is a magnet. It attracts metal on both ends, but when you bring two magnets close together, opposite ends attract and like ends repel. Wait a minute, that sounds exactly like what electrical charges do. The negative charges in the electrons are attracted to the positive charges in the proton in the nucleus. Exactly. And it was this observation in particular that led James Clerk Maxwell to determine that electricity and magnetism were two manifestations of the exact same phenomena. The word magnet comes from the Greeks again. They stumbled across amber electricity, and then they stumbled across one of these. A lodestone rock. It's a naturally magnetic rock, attracting metals and apparently was found in abundance in a place called Magnesia, Greece. A magnet is an object that creates a magnetic field, a mysterious force that repels the like poles and attracts the unlike poles. Every magnet has two poles, which we call north and south. If you break a magnet in two, quite mysteriously, each piece will again have a north and south pole. It has never been shown to be possible to have a single pole magnet. And why do they attract metal? Well, it isn't absolutely certain why magnets behave the way they do. But the most prevalent theory is this: that electrons themselves have an orientation that is magnetic, even though they are negatively charged particles, that they each have a tiny magnetic field, and no one knows why this is, but scientists call it the electron's spin. When someone asked the physicist Richard Feynman why magnets behave as they do, he said, "I am not going to be able to give you an answer as to why magnets attract each other, except to tell you that they do." Here is an atomic view of a non-magnetic metal, say copper. You can see the individual atoms here forming individual magnetic areas or domains. The combined spin of all the electrons give each domain a magnetic direction, and they're all random and pointing in any direction. The result is a non-magnetic piece of metal with each domain canceling out the areas of the other domains. But in a magnetic metal like iron, the domains can be influenced by a strong magnet, twisting the domains until they all point in the same direction. The result is a magnetic piece of metal with all the electrons spin oriented together and making a strong magnetic field. That's the theory, and it doesn't answer all the questions, but at least it gives a model as to what might be happening at the atomic level with magnets. Not all metals are attracted to magnets. Gold, silver, copper, aluminum, they're completely unaffected. But iron, cobalt, and neodymium are all strongly attracted to magnets and can be made into permanent magnets. Man-made magnets. Really strong magnets. If you heat up a magnet, they will lose their magnetism. If you hit them with a hammer, they can lose their magnetism. Apparently, the heat or the shock causes a disorienting of that electron spin. One of the first things people did with magnets was to make compasses out of them. If you stroke a lodestone or a magnet over a needle in the same direction about 10 times, you will orient the needle's magnetic domains in the same direction, thus magnetizing the metal. Then they would float the needle or suspend it from a string. And the needle always pointed in the same direction. Putting a magnet in the path clearly reorients the needle. All kinds of ideas developed as to why this was the case until this man, William Gilbert, built a magnetized needle that could point up and down as well as back and forth. Gilbert positively proved that the Earth itself was created as a gigantic magnet. He concluded that one pole is in the Arctic and the other one is somewhere in the Antarctic. And the only reason compasses work at all is because we are living on a gigantic lodestone hurling through space, a 6 sextillion-ton magnet. You can literally see magnetic fields using this acrylic case with iron filings suspended in oil. Put a strong magnet underneath it, and the iron filings line up with the magnetic field. There is one of these around the entire Earth also. The Earth's north magnetic pole is currently right about here, and oddly enough, the magnetic pole has been moving toward Russia about 40 miles every year for a century, possibly due to the shifting in the Earth's iron core. Magnetic north is now about 1,000 miles away from the Earth's geographic North Pole. Positives and negatives, attracting and repelling. Electricity and magnetism are definitely linked. Electricity and magnetism are linked. If you have electricity, you can make a magnet. If you have a magnet, you can make electricity. If you have a magnet and electricity, you can turn a motor. This was one of the major discoveries that allowed electric motors to be made. Motors that revolutionized industry and allowed electricity to be carried from house to house to house. Michael Faraday was really the man who worked tirelessly for over a decade trying to generate electricity from magnets because he, and many others, just knew there had to be a connection. In 1821, almost 200 years ago, he finally succeeded in proving that the relationship between electricity and magnetism is motion. And we can follow what Faraday discovered. First, we will turn electricity into a magnet. We will need an electric source, this fresh D-cell battery, an iron nail, about 3 feet of electrical wire, small gauge, and maybe a few paper clips to pick up. Wrap about 3 feet of wire around the nail and strip the ends of the wire bare. As the battery produces an electric current, a corresponding magnetic field will also develop, and the wire will tend to get a little warm, so you may wish to tape this side to the bottom. And if you set a compass on the wire, you can see that a magnetic field is being created as the compass responds and tries to orient itself to the new magnetic field. Faraday then worked on taking magnetism and making electricity. The breakthrough came when he realized that the missing ingredient was motion. What was needed was actually moving the magnet or moving the coil. We can simulate Faraday's discovery, make a coil of coated wire, and then wrap or tape the ends so it doesn't unravel. We will use an inexpensive compass since it will respond to a magnetic field. Wrap the wire around the compass a few times. Then tape the wire down and connect the bare ends so the circuit is complete. The movement in and out of the wire coil actually forces the electrons in the wire to move back and forth, and that action produces an electromagnetic wave which the compass detects. And finally, we will take electricity and magnetism and make motion. In other words, we'll make a motor. The word motor literally means a mover. Remember, it took Michael Faraday over 10 years to figure out how this thing works, so it might take a little patience on our part to get it to work right. You will make another coil of wire, but just a little smaller. Strip the entire plastic off one end of the wire. Then, using a razor, carefully strip only half of the wire off of the other end, so that the top half is coated and the bottom half is bare wire. This is important as it makes a break in the electromagnetic field, effectively turning it on and off. A few rubber bands around the cups will hold your paper clips, and you can put a little bend at the top with a loop in it. You can either tape one magnet down on the cup or use a second magnet to hold the top magnet in place. Then put the wire loop in the cradle and adjust the ends so it can spin freely. Once you put it together, you get a really good feeling of how these invisible but very obvious fields are working. Keep working with it. If it doesn't spin right away, play around with moving the magnet to get it just right and moving the paper clips. Once you connect the wires, you can see how the coil of wire is attracted to the magnet. These two fields, the electric field and the magnetic field, are working together to pull the copper coil in a circle. It will only want to spin in one direction. A motor takes electric current and turns it into circular motion. That can be pretty useful for things that run off of motors like drills and trains and electric cars. Our little motor here is not a very efficient use of the voltage, and the charges will balance out pretty fast in the battery. You can even feel the battery getting warm as a lot of the energy is wasted as heat. The incredible thing is that by taking a magnet and a battery, which don't move, you could turn it into a machine that does move. From this simple motion, you could make bigger, stronger motors, ultimately making just about any machine on the planet. James Clerk Maxwell was working on electricity and magnetism and noticed that they both travel at the speed of light. A few years later, Heinrich Hertz built a machine that generated what we call radio waves, and they too traveled at the speed of light. 10 years later, William Röntgen discovered X-rays, a kind of wave that would penetrate skin but not bone, and these too traveled at the speed of light. And finally, about 10 years after this, William Bragg demonstrated that the recently discovered gamma radiation was not particles but waves traveling at the speed of light. And it was primarily this common speed that began putting the puzzle together, that these seemingly different phenomena were all in fact the same wave energy, but just different lengths of wave. The spectrum was sort of a map of how all these apparently unconnected discoveries fit together, almost like a periodic table of wave energy. At the far end, the waves are miles long, very low frequency. And at the opposite end, the waves are tight and tiny, drilling in with an almost frightening frequency, able to penetrate virtually all matter. These waves are shorter than individual atoms. But at one tiny point in between these extremes, the waves suddenly become visible to our eyes, and they look red. You literally see the electromagnetic spectrum. As the waves continue to get smaller, they turn orange, yellow, green, blue, then a faint violet. Then suddenly our eyes can no longer pick up this frequency, and the spectrum disappears once again from our sight. That is the visible part of the electromagnetic spectrum. They are identical to radio waves, just a different frequency. One of the difficult parts about the electromagnetic spectrum is getting your head around the idea that it's all just one wave with different frequencies, so that when you hear radio waves, you automatically think of radio and music. With microwaves, you think of a microwave oven, and X-rays, well, that comes from the dentist office. But we identify these certain parts of the electromagnetic spectrum with these things only because those frequencies happen to be very useful in those applications. It's kind of like certain elements on the periodic table of elements are good for some things, but not good for other things. Gold is good for coins and teeth fillings, but not so good for building bridges. The electromagnetic spectrum is kind of like the periodic table. Certain frequencies are very useful for certain applications, which other frequencies aren't good at. At the farthest end, there is just one wave per second, 1 hertz. And since it's traveling at the speed of light, 186,000 miles per second, the wavelength is 186,000 miles long, which is very, very long indeed. This is super low frequency, 1 hertz, and it is virtually useless to us and almost impossible for us to generate. The first really useful frequency on our electromagnetic spectrum is at about 60 cycles per second, or 60 hertz. This is the frequency of the wave going down power lines. You can even see on your appliances that they operate at about 60 hertz, 60 wavelengths every second. Now, we often show power line graphics with lots of tiny waves going down the line just to show that the waves are in fact really there. But in reality, power line waves are huge, over 3,000 miles long each. That's longer than the entire continental United States, going by at the speed of light. That's so long that as the wave goes by your house, it is virtually flat to us. The next really useful area on the electromagnetic spectrum happens at about 100,000 hertz, which is still considered low frequency. These waves are roughly a bit longer than the Golden Gate Bridge in San Francisco, California, and they have the ability to reflect between the Earth's surface and the atmosphere, following the curve of the Earth. That makes them pretty useful for certain limited military and civilian radio communications around the world. When you get to higher frequencies, about 1 million cycles per second, 1 million hertz, roughly as long as a football field, and these cycles are frequent enough where you can start embedding complex information in them, like voice and music. One section of this frequency goes by the common name of AM radio. If you increase the cycles to 100 million, roughly the length of an average house, you encode even more complex information and you can broadcast stereo music, FM radio, and broadcast moving pictures, television. Higher frequencies become so energetic that at about 2.5 trillion cycles, you can talk on your cell phone using only 1 watt of power. With 2,000 watts of power, you can use this frequency to cook food in your microwave oven. These waves are roughly the length of a baseball. Once we get past a few trillion cycles per second, the waves are coming in so fast and are so small that they are no longer very useful for radio or television communications. At this tiny frequency, most scientists stop using Hertz frequency measurements and give the length of each wave in nanometers, a billionth of a meter. A sheet of paper is about 100,000 nanometers thick. Just before the color red, there are tiny but energetic infrared waves, just barely outside our ability to see them, but energetic enough that we feel their energy as heat on our skin. Although all parts of the electromagnetic spectrum produce some heat, this part is particularly effective in heating objects. The heat from your stove, a fire, a match, or the warm sidewalk. That's infrared heating from this part of the electromagnetic spectrum. Then visible light. A single red light wave on the electromagnetic spectrum is about 700 nanometers long. X-rays get even smaller, as small as 1/100th of a nanometer, or about 1 quadrillion waves per second, energetic enough to penetrate skin, but not bone, giving us X-ray pictures. And then, at the far end, high-energy X-rays and even more frequent and more energetic gamma rays are small enough and energetic enough to break chemical bonds and remove electrons from atoms. Both X-rays and gamma rays can knock electrons off or ionize atoms, but gamma rays are far more energetic and dangerous. Contact with these absurdly small and energetic rays can cause burns, cancer, and even death. That is the electromagnetic spectrum, similar to the periodic table of elements, but instead of elements, a whole spectrum of useful, vibrating electric energy waves. Electricity and magnetism allow us to make things that move, that light, that heat, that make our world wonderful and comfortable. In reality, we take our electricity and magnetism for granted. But we shouldn't. Over 1 billion people still live in the dark, without light, and without electricity and modern cooking and modern heating solutions. We should take them, along with every other gift we've been given, with a proper amount of humility, gratitude, and thanksgiving.